This is another easy integral. Now I have two methods to do, so I want to share with you. This is these are great these are great methods. Now the first method, I leave 1 over x out and consider the numerator as a log of 1 minus yx. Y is from 0 to 1, then dx. Right? When y equal to 1, it's a log 1 minus x. When y equal to 0, it's log 1. Log 1 is 0. So it's equal to numerator. Now then this one is just definite integral, right, from 0 to 1. So this is equal to 0 to 1. This is this. And x, this is this, right? Then that one is considered as a 0 to 1. From 0 to 1, the 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 integral function is the derivative of that, right? Because this is the antiderivative of this. This is the antiderivative of that integral function. The integral function is the derivative of this one with respect to x, which means equal to 1 minus yx, because I take a derivative with respect to y, so it must be negative x on top. Yeah, and then dy. Yeah, that is this, right? Then dx. Yeah, very good. Then this one equal to 0 to 1 and 0. It's a double integral. We can switch the order. And I first change this one, change it negative by switching the order, right? It becomes a switch that minus 1. Yeah, sorry. There's a positive. Then to x first, then y. Now, when we do integral with respect to x, then y is constant, right? Constant. Yeah. So then this one equal to 0 to 1, 0 to 1, and x plus 1 and a, right? Plus yx minus 1 and b, and dx, then dy. Yes, yeah, that is okay. It's okay. Then the partial fractions were a yx minus 1 plus b x plus 1, which is equal to x, right? So ayx plus bx is equal to x. Negative a is plus b is equal to 0. So a must be equal to b. Put an a here. So a is equal to 1 over y plus 1. Oh, we find both a and b. So AB is a right when we integrate with respect to x. So y plus 1 is a constant, right? And then this is an integral of right x plus 1 plus yx minus 1 dx dy. Okay, I don't want to write, make a mistake here. So this one equal to, there are two integral, right? One is 0 to 1, 1 over y. This integral is a log x plus 1, x from 0 to 1, right? Then take care of a dy. Yeah, that is this one, times this one, plus integral y, this. This integral with respect to x is what? This integral, this integral dx over yx minus 1. This integral is equal to log yx minus 1 times, because y is a constant, so 1 over y, right? Yeah, that is right. This, something like this. Yeah, okay. So becomes y log yx minus 1 from 0 to 1, right? Then dy. Correct. This is for x. So this one is equal to, this is log 2, right? Log 2. And this one is equal to log 1 y plus 1 from 0 to 1. Yeah, that is this one. Then this one plus 0 to 1. I write y first, then y plus 1. This is for x, is a log y minus 1 minus, when x goes 0, is a log minus 1 dy. Wow. Okay, so this one equal to log square 2. Now, this one, I have to solve the problem of the negative one here. So this one, this is a log y minus 1 over log minus 1, right? This is this. So this could be log 1 minus 1. Yeah. This is log 1 minus 1, right? So this becomes a 1 log 1 minus y over, wow. Yeah, the picture is a little clearer. So this was a log square 2 plus 0 to 1 log 1 minus y. This will consider the partial fractions, right? Y a plus y plus 1. And here, let me omit the determination of AB. A is a 1, B is a negative 1. Yeah, so this one's a log 2 plus, here. So integral, there are two integrals. One is a y log a equal to 1, b equal to negative 1. This is the work I've been omitted. So now this is 1, right? So log 1 minus y dy minus, because this is negative, from 0 to 1, log 1 minus y. This is y plus 1 dy. Wow, very good. Now, then this one is same as my target integral, right? I. This one and the other one the same. Well, x might just dummy variable, right? So if we move over there, the 2r is equal to natural log square 2. If I move over there, 2i, right? Equal plus 0 to 1 and natural log 1 minus y dy. Wow, the picture is clearer. It's much better. Now then, how do we solve this one? Well, let's take care of this one. 0 to 1 log 1 minus. Okay, now we are focusing on the final step. That is this one. And well, we are using this because a log of 1 minus y is equal to negative sigma 1 to infinity yn. Well, if you don't remember that one, wow. Now let me show you how to find this, the Maclaurin series of a log 1 minus y. Now let's just start with this, right? This one is just power series. It's a negative is equal to yn, right? On from to infinity. Minus 1. You know, yes, I think correct. Then both sides integral. This is a negative log of 1 minus y. This is the integral of this one is this. The integral of this one is equal to integral this one with respect to y is equal to yn y squared, right? Yeah, that's it. Therefore, log of 1 minus y is equal to negative sigma n y. Yeah. That's correct. See? That is what I have here. Now then this one equal to integral negative, huh? Negative sigma yn over yn dy from 0 to infinity. Wow. Then this is negative integral. This is sigma yn minus 1 over n dy. Now, for this series, in this interval, it's convergent. If you do the test test the convergence and find the radius of convergence. So 0 to 1 is okay. So we can switch the operator. So it becomes minus 1 to infinity and 0 to 1 and y minus 1, right? dy. So that integral can be done. It will negative. This is y squared, right? Yn. Yeah, from 0 to 1. So this one equal to negative 0 to 1 is right. 0 is a 0 gone, so this is equal to negative pi over 6. That is Basel. Therefore, 2I is equal to net log 2 minus pi over 6, right? Because this one is equal to pi square over 6. Then I is equal to half log square 2 minus 12 pi square. Wow. Finally, we have a big conclusion, big result. Well, it's a nice method. Now, this is a method of 1. Now, let me do by method of 2. Method of 2, 0 to 1 log 1 minus x plus 1 dx. Now, method of 2. I start with substitution. Let t be 1 minus x, 1 plus x, sorry. T is 1 plus x. Then 1 minus x is equal to 2 minus t. Okay, so my integral becomes t log 2 minus t. dx dt, same. So dt. When x equals 0 is a 1. When x equals 2. Yeah. Good. Now then, well, now here, I want to express log 2 minus t into a series. Now, how if you don't remember all the details, now let me do the primitive way, start from beginning. So this one could be easily just 1 divided by this one. You get the series is a 2 to the n t minus what? Very easy. Just divide this one by that. You get this. Then both sides integrate with respect to t. So this is log 2 minus t. This integral is equal to integral 1 from n to n minus tn. Wow. So that is the expansion of log 2 minus t. So I can do this one as a negative right? Sigma 1 to infinity t, I forget, okay, t to the n, t to the n, and over here, well, another t, and 2 minus 2 to the power n, and dt. So this one is equal to negative 0 to 2, sigma 1 to infinity, and t n minus 1. There's n here. I'm sorry. There's n here. N 2 to the n. Yeah, dt. Okay, there's n here. Now, then, of course, I want to switch the operator, right? Then finish the integral very easily, and we can get a result. But unfortunately, we are not allowed to switch the operators because this series is not convergent in this interval. Well, you can do by test of convergence. Look, well, when t equal 2, t equal 2, right? So this one is the same thing as this one. They're equivalent. Then leftover is a 1 over n, the series, which is a harmonic series, is a divergent. So this is a divergent series. We cannot switch. We cannot switch the operators. So we're stuck here. Well, we have a problem here. We cannot switch. Now, how to solve this problem? Well, let's go back to here. Well, I try to remove this t, remove this 2. No. Okay, let me consider this one. Let me go back to 1 to 2 lateral log 2 minus. Well, let me change the t for x again because these are just dummy variables. Now this one has a problem when this is 2 because we cannot switch the operators. What to do? So let me do something here. I can do this, can I? 2, 1 minus x over 2. X dx. Yeah, that's okay. So this one equal to natural log 2 over x dx, right? That's the first part. And the plus 1 to 2 log 1 minus x over 2. Can I write dx into 2 times 2 x over 2? Yeah, yes, I'm allowed, right? This is the same thing, dx. And I write x as a half x times 2. Yes, they are same. So they're equal. Now this one is equal to log 2 log 1 to x, right? That is easy. Now for that one, I check u is equal to half x. U is equal to half x. Then this is a log 1 minus a u, right? 2 cancel out. This is a du. This is a u, right? And when x equal to 1 is a 1 half. When x equal to 2 is a 1. Wow. This is a good, because that one change to series becomes convergent. So this is equal to log square 2, right? Very good. That one, well, is half to 1. Well, I don't like a u. I like x. Let's change the dummy variable. Same thing, x, right? So this is dx. All right, now something happened. Uh, log 1 minus x is equal to negative. Well, this we have done last case, right? All very easy. You can develop this one into a series. So this one is equal to log square 2 plus this one. This one, I rewrite this for this one, place it here, right? So it becomes negative, and this one over this becomes x minus 1, right? And x, yeah, yeah. Very good. Series, a power series. 1 to infinity. Yeah. Now this series, is a convergent, right? Between half and 1. Yeah, now we can switch this one equal to sigma from 1, then integral half x squared. Yeah, this one is equal to negative. This integral is equal to n squared, right? X. Yeah, equal to log square minus n square 1, right? Plus n square half a square. Yeah, that's right. I forget sigma notation. Sigma. I forget a sigma notation. Excuse me for those. Okay, this one is a log square 2. This one is a Basel problem. This is pi over 6. That one is a logarithm function. This one, okay, square n square. This is a logarithm function which is equal to pi square over 12 minus half log square 2. Yeah, something like this. Well, if you can change, you check the information on internet. This is a logarithm function. Well, so this one is equal to plus pi square over 12 minus half log square 2. So eventually this one becomes a half log square 2, and this one minus 12 pi square. Well, we get the same result by this method. Excuse me, there's a messy writing, and I think you can trace easily all the details. Well, it's interesting. Thank you.